Welcome, everyone, for my talk, and thanks to organizer for inviting me. It's a big pleasure to be here, and it was really great to listen to Jeff and Jung Chu's talks earlier today, and those two provide a very nice introduction to my talk. So I slightly changed the title of my talk because I decided to take a little bit broader angle compared to just diffusion model-based angle. So I'm going to talk about the plug-and-play priors. So some of you might know it, some of you might not know it, but it's a framework that has been introduced by Charlie Bauman and collaborators by using denoisers as regularizers for inverse problems. So if you think of diffusion models, you can clearly see analogy between the two approaches. And essentially, diffusion models can be seen or interpreted as an extension of it to turn them, the plug-and-play priors, into generative models. Okay, so I'm going to explain this all to you now. And as we already saw, diffusion models or using of denoisers for generative purposes has really transformed the way we think about images. And it did fundamentally transform the way I think about images. And here are some very impressive examples where you take a text prompt, you plug it in, and you get an image. And all of those are impressive. But the key thing here, which really I take away, is the fact that the sharpness or realistic ability of those images, right? So you take a very little input, which is a text, and then you get something which is very high dimensional, but also very realistic or sharp looking. And that was something that I liked from the beginning. So the topic I'm going to, of course, talk about will be very much related to the previous two talks, and I'm going to talk about imaging inverse problems. So inverse problems basically means I have a forward problem where I have an unknown image which gets mapped to some type of measurement, and the measurement comes from some kind of physical models that I know that's represented here by a sensor model A, right? So I know this A, maybe up to some parameters, and then there is some uncertainty, there is noise. So now we have measurement Y, but what we really want is X. So the inverse problem is going back to X, okay? So this is something I've been working for quite a bit, and of course, Jeff's work has been a big inspiration to me over the years. The reason I like this formulation from the very beginning is that it's general. By writing one simple equation, right, the forward model, now you can start looking at all kinds of different applications. And in particular applications I'm very interested in, which are biomedical imaging. And this is something that I've been very interested in since a long time. So let me give you 3 examples that I'm going to talk to you about today. The first is something we've heard already about. It's a magnetic resonance imaging. So in MRI, where we collect the data is in the frequency space, which is also known as K-space. But what we do want is an image space. So we don't directly get the image space, unlike photography, right? We have to collect data indirectly and sequentially, and then when I take inverse Fourier transform, I get the image. Now, there is a direct relationship between the time of data collection, of course, and image quality there, because we're collecting indirectly and sequentially the data, and this gives me image. So the goal here might be multifaceted, but one of the goals is trying to shorten the data acquisition because it would directly improve patient comfort without compromising the imaging quality, right? So here's one example that I've been working on. So this is a whole body MRI. If you get a full scan, you would get something like this. But if you want to try to accelerate this full scan to 1 or 2 minutes, you're going to start seeing this, the streaking artifact. This is a radial acquisition, which means you see the streaks. Now, the one interesting thing here is it's a breathing, right? You can see this one slice, and a person there is just breathing. And as the person breathes, we collect the MRI. Another application I'm going to talk about is going to be limited angle tomography. It is related to MRI, but the collection is not in the K-space. What we do collect are projections of the image. So here's a little illustration. Here I get more and more angles, meaning I take projections. S represents the sensor array. So by adding more and more on projections, it's a parallel beam setup. I'm going to get an image here by taking a filter back projection algorithm, which takes the measurements back to the image space. The key to notice here is that if I have very few angles here, I'm missing a lot of information, so the image will be inaccurate. And that's where I'm going to talk about using diffusion models to fill in the missing data by trying to generate it in the extreme cases. So here's a little illustration. So this is a suitcase. You can see we're going through the slices of a suitcase. If I would collect only 60% of the angles, so I'm missing 120 degrees out of 180, then I would see something like this, which is, it's impossible to even recognize it's a suitcase. But, of course, I would want to have something like that. And finally, the third application will be in the bio domain. It's going to be microscopy. So it's a microscopy technique known as intensity diffraction tomography, which is a very simple setup. And this is done in collaboration with Lei Tian at Boston University. So we have a light source which consists of LEDs. There's a sample, some objective, optical setup. And finally, we get a digital camera, which is essentially a CCD. We lost my slides. No, they're back. All right. So the way IDT works is we illuminate one of the LEDs. The light goes through the sample. It goes through the optics, and we collect intensity measurement for that single LED, right? So what I can do now is illuminate another LED, right? If I illuminate another one, the light goes through, interacts with the sample, and I get another measurement. So we can collect hundreds of those by illuminating different LEDs. And the goal is, once I illuminate all these things, can I solve this inverse problem to recover the 3D sample? And in particular, what I want is 3D distribution of the refractive index of the sample. So for every location in a 3D sample, what I would want to have is a real and complex value, which is going to be the corresponding to absorption and scattering, which is a refractive index. Now, by looking at it, I can see the cells and try to do something. So it's a 3D imaging technique here, and this will be the third thing we're going to talk about. So, of course, all those settings come with issues, which are very well known in the inverse problem community, and those are the things we want to address. The first issue might be acquisition might be too slow or costly, sequential indirect acquisition of the data. Reconstructed images contain artifacts, so you can see all three types of, so this is IDT sample. You can see there's missing angles, so there's a low axial resolution. And finally, high computational memory requirements, especially if you go to 3D samples, right, XYZ, 4D XYZ time, 5D XYZ time spectrum, and so on and so forth. We could try to push it to higher and higher dimensional data. All right, now how can we try to address this? The angle I'm going to take is going to be based on image probabilistic formulation, bringing image models, right? That's a very conventional approach. So what we do typically, well, we say, oh, we know the forward model, so I write out the forward model, and we usually know something about the noise model. We can measure it, model it, or we assume it. So this is a basic assumption here. It's a Gaussian additive white noise model. Now the key here is, what do we assume about the unknown quantity? And that's where a lot of innovation has been happening in the context of inverse problems, where what can I say about this? So we're just going to assume it is some probability distribution. Now, the whole art, as you saw at the Jeff's talks, is like, how do you model it, right? How do we get it? Well, there are a few things we know about images, okay? We know that they're high dimensional very often, except if you do like a low dimensional setting. And the second thing you know is that they're compressible, meaning if you have n by n image, usually you can press it to the volume, which is much smaller than n by n. So a lot of people interpreted saying that images live somewhere on a manifold or in some kind of union of subspaces, or there's kind of parsimony model underlying images, which gives us hope that maybe we can do something about it. But still, even if you understand this thing, the question becomes, how do we actually represent the space or manifold of images? And that's where the innovation is. But let's suppose for a second that we can get some kind of magically the prior distribution of images. Well, now I can do all kinds of interesting statistical things. I can just write a statistical estimator, for example, a map estimator. So you see here on your screen a map estimator. I put the data fidelity term based on a Gaussian distribution and a prior. Somehow I have it. I'm going to try to solve this optimization algorithm, and a solution from this will give me a solution, a most probable image given my model, right? Now, a special type of inverse problem is an image denoiser, okay? So an image denoiser is an inverse problem where now instead of having A, I'm going to put identity, and I can still write it out in this form. And the whole argument around diffusion models and plug-and-play priors has been around the fact that denoising can be a very powerful proxy for representing prior information. So what it basically means, maybe you don't need to model the whole PX. If you have a denoiser, now you can do all kinds of operations beyond denoising, right? And that's what I'm going to talk about, and it's based on plug-and-play priors. So this was a quick introduction. I'm going to talk about basically 3 approaches. In fact, the first one is quite related to Jong-Chul's work on blind inverse problems. I'm going to talk block coordinate plug-and-play method, which is going to try to do denoisers, not only images, but also on the unknown forward models. Then I'm going to actually talk about diffusion models, trying to fill in missing information in limited angle CT. If I have time, I'm going to try to go into implicit neural representations by having continuous representation of objects and still using denoisers as priors in that case. All right, so let's get started with the first one. So block coordinate plug-and-play methods. So I'm going to quickly first start by reviewing plug-and-play methods. If anybody is interested, there is a tutorial papers that came out in Signal Processing magazine this January that can give you more information that I will have time to review. But the basic idea is very simple. In the basic idea of plug-and-play priors, first thing we do is we're going to try to get the prior. How do we get a prior? We're going to just train a denoiser. How do I train a denoiser? I'm going to take an image of type I want. I'm going to add noise to it, and I'm going to train a neural network to remove the noise from it. That's it. I'm going to add different levels of noise, train a neural network to try to remove this noise. And of course, this gets us very nice statistical interpretation, because if I train this, for example, by using L2 loss function, so it can be interpreted as an MMSE function, then I could say, oh, you know, I can use a Tweedy's formula, try to get information about the gradient of the graded observation, which can be related to the gradient of a prior convolved with a Gaussian distribution, right? But another thing, that's what Jong-Chul mentioned, is that the plug and play, so the prior, is not trained on a task we want to solve, fundamentally. It's trained on some other task. It's a denoiser. But I want to solve something else, right? So I'm just training a pure denoiser. Now, here comes the second, and we typically train it at the different noise levels. And by the way, this was something which diffusion models really changed in the way I approach this thing. It's better to train on a wide range of noise levels to get the prior, right? So we train different, and interpretation is as you take get the denoiser trained on a higher noiser level, it puts kind of more prior information in it. That's one of the interpretation we can do. Now, the second key part for inverse problems, now we need a forward model, the physical model, right? There are several ways to implement it. For example, one easy way you could do, you can say, oh, you know, I have a Gaussian model. I take a least squares, and I do a simply gradient step with this. So this one just takes a gradient step from less measurement consistent to more measurement consistent. And basically now you can write plug-and-play priors algorithm. So this is one of the versions of plug-and-play priors algorithm, which simply takes a gradient step with respect to the forward model and then denoises. And you iterate this algorithm until you get somewhere. So here there's no stochasticity in this algorithm, right? We're just iterating until some fixed point. All right. So this turned out to be pretty powerful approach. The reason is there's a lot of mathematical work around it. There's mathematical elegance. There's modularity. We separate the physics of the forward model from whatever learning aspect. It's self-supervised. And finally, it can get a pretty impressive performance in many applications. So for example, I can give you one illustration of the performance of this. This is for a 3D MRI reconstruction. This is actually my head. So maybe you can recognize me from this reconstruction. So this data was acquired over 1 minute, 12 seconds, right? And then if you compare it, for example, to a traditional graph approach, you can see the training denoisers and using there works quite well. Now, one thing I'm not talking about this yet here, this algorithm also has auto-calibration inside. And this is something I'm going to talk about next. So far I just talked about the priors. But in fact, to get a better performance in some applications, you also want to use priors for calibration purposes. All right. So what I'm going to talk about now is a relatively recent paper. It's called Block Coordinate Plug-and-Play Methods for Blind Inverse Problems. And then let me explain this. So basically, the idea is very simple. Now, just like Jong-Chul's setting where he explained, we have 2 priors. We have a prior on the unknown image, and we assume there is a prior on the measurement operator. Okay, there are 2 things that happen together. And then idea is, well, applications. So we saw the application on the blind deconvolution. But in the MRI, it could be the same thing, where now the unknown parameters or unknown forward model will be coil sensitivity estimates of the MRI system, right? So we have a prior on the image, and we have a prior on the coil sensitivities in parallel MRI. All right. So the way we're going to approach this problem is as follows. We're going to just take a block coordinate interpretation of it. We're going to say each unknown group, so maybe one coil sensitivity, an image, or a blind blur, right, is going to be a block in the vector we're trying to estimate. So each block has its own dimensions. If I add it up, this will give me my total unknown vector, right? So for example, if I have just two parameters, like image and a blur, I would have X consisting of two blocks, okay? The next thing we're going to do, we're going to define block gradients and block denoisers. For each block, we're going to train a denoiser, its own denoiser. So I'm going to train a denoiser for coil sensitivities. I'm not going to model them. I'm going to just purely train a neural network to add noise to some sensitivity maps and remove it, okay? And we're going to do the same for images. And then we're going to impose a data fidelity term by just putting a gradient with respect to data fidelity term for each parameter. Okay? And basically from there on, now once we have these two things, now we can run a plug-and-play algorithm very easily by doing update of one block at a time. So in the case of blind blurring, I could update the blur, and then I update the image. I update the blur, I update it. In the coil sensitivities, I alternate between coil sensitivities and images, and we just alternate this thing. And if you have more blocks, you can just run more block. So here you can see the block selection. I didn't specify it, but you can do a random block selection, or you can do sequential block selection, and this will change a little bit the theoretical analysis that I'm going to show, but not significantly, just like in traditional block coordinate algorithms. All right, so let me just give you just a little illustrations before I give you a theoretical interpretation of this. So this is an illustration how iterations work. So on the left-hand side, there's estimated algorithm for MRI. So this is six-fold acceleration in parallel MRI. This is a ground truth image. This is ground truth coil sensitivity map, which means it was estimated from the clean data. And this is estimated coil sensitivity maps. As you can see, the using trained denoisers can actually impose or learn the structures both of the image and forward model and try to get very close to the Oracle plug and play where we do know the coil sensitivity maps. There's much more experiments in the paper, and you can also apply it for blind blurring. This is for blind blurring where plug and play here refers to when we don't know we have a fixed coil, the blur kernel. If you run that algorithm, of course, you're going to saturate, but if you update also the blur kernel, you're going to also be able to update the blur kernel to the performance. Yeah, so anyways, you can go to the paper to see a lot more experiments and comparisons with all the algorithms, but the point is you can define image denoisers as priors easily beyond images. It doesn't have to be images, and in particular, it can be very effective for modeling the forward models. One interesting thing in all these experiments is that the algorithm itself is extremely stable. There's no stochasticity here. It converts, except when you pick the blocks, and the convergence is pretty stable and without any issues. And of course, you can make a very precise statement about convergence behavior of this kind of algorithm. So if I assume that my denoiser, so this is a statistical assumption, is approximately MMSE estimator, so which means it performs something like MMSE estimator, and there is some error factor here. So I assume my neural network is performing this kind of operation for denoisers, and I run this block coordinate algorithm under some Lipschitz continuity assumptions. Then you can show that the algorithm itself will be converging to a stationary point of some loss function up to an error term, right? And this error term will basically be the errors, average errors you're making with respect to the true MMSE estimator, okay? So you have a neural network which approximates it, you're making a little bit of error, and then final error will be an average of that quantity over the iterations. And here, what you see here, the loss function is an interesting loss function. It's going to be dependent on the denoisers that use it, but it's not, typically it's not equal to negative log of prior. Okay, so it's not equivalent to negative log of px. There's an expression for it. You can find the expression in the paper if you're interested, or I can talk to you more about it. All right, so that was a the first thing I wanted to present. So what did I talk to you? Well, I talked to you about block current algorithm where we can train a denoiser for any unknown. We take the forward model of the inverse problem, and we put it together to try to recover this thing. The key here is that it's both priors are trained in a completely self-supervised way. So the next thing I want to talk about is a version of diffusion models for CT reconstruction, and in particular, addressing the issue of plug-and-play priors in a traditional form where you have very limited data. So in particular, I'm very interested in a setting where we're missing a lot of data. So for example, we have only 60-degree angle out of 180, so we're missing all this 180 degrees. So we have this, right? And if I do filter back projection, I would get these two images. And you can look at those and try to guess what those are. I can tell you this is a suitcase and this is a human body, right? But it's very hard to guess from this amount of data, which tells you that's very little you can do. If you would try to run a denoiser as a prior, just the way I explained to you, it wouldn't be able to recover it. Okay, it wouldn't be able to recover it. You would get this kind of blurry images for both. So you can see this one is for the human body, and this one is for the suitcase image. It can get something, but there's still a lot of missing. What you do need here is what diffusion models brought to the table, right? And this is the ability to sample stochastically. And this is also a paper which is going to be presented at ICCV very soon, in maybe a couple of weeks. But the key idea here is the same as in plug and play with a little twist. So, and there's also a little twist with respect to a traditional diffusion model for inverse problem like DPS. Okay, so what we do here is we're going to train a denoiser, all right? But the denoiser, we're going to do a conditional denoiser that not only takes a noise level and a noisy image as an input, it also takes the sensor data as an input. Okay, it has two channels. The second channel is back-projected sensor input. Okay, the output, well, here we're predicting noise because by just simply adding the noise, I can denoise this thing, right? So this is noisy input. If I predict the noise and I would subtract it by the same amount, I would get a clean image. Essentially, we're still learning a denoiser, but that denoiser as one of the inputs has a sensor data. Okay, and we train a denoiser in a similar way for different noise levels. The C is here, fix the center data, but we basically train it to be MMSE estimator for different noise levels. Okay. Now, that's first part, the learn part. The second part is a physical model. The physical model would simply be the CT model, but we're going to implement it instead of a gradient. We're going to implement as a proximal operator of the measurement model that we have, and it just takes us from less measurement consistent to more measurement consistent. And finally, we're going to just put it into the diffusion model framework where I have a conditional denoiser. At each iteration, we're going to generate some stochastic sampling, and we're going to put data fidelity term as a proximal operator, and we're going to iterate this algorithm. You can also represent it in this form where we go from more noise to less noise by taking noise down, just like it's done in diffusion models. So the only change here will be that each iteration will have a sensor input as a constant input to the model. All right? So what's interesting is now we can actually run this algorithm, right? We run this algorithm, and it will generate, unlike plug-and-play priors, very sharp images. So you can see those are different images generated by the algorithm. It's a stochastic algorithm. You can notice that each image is very sharp, but it could be wrong, right? So if you look at this images here, those are the suitcase images, two samples, distinct samples from a suitcase image. Each one is wrong if you actually look at the ground truth suitcase image, right? But each one looks pretty realistic. So this one is a little broken here, but so each one looks realistic, but they're both wrong, right? But one thing you can do is you can take many, many of those, thousands of those, and try to generate a variance map to see where those differences are happening. And that can give you some form of explanation of uncertainty where you should watch out for your model's generation ability. And you can see it kind of aligns with this region in this case, which completely makes sense because that's where we have a missing data in the measurement. So that all part is essentially synthesized by the algorithm. And this method, Dolce method, there are a lot of experiments in the paper. You can look at it. It really gets you a state-of-the-art algorithm. Now, the reason it gets such a good performance, SA here, by the way, this is a method for different measurement angles, PSNR, SSIM, compared with different algorithms here, including plug and play. But the one thing to notice, so SA here stands for averaged algorithm, which means we take a bunch of samples, thousands of samples, we average them, so we can interpret as MMSE, and then this one just means we pick one sample and we just present the result for one sample. And of course, we can now run it for generating 3D suitcases. So here you see the ground truth. This is a generated algorithm. This is total variation. This is filter back projection. You can see it gets very realistic, sharp images. This is for 60 degrees, and this is for 90 degrees missing angle. And here you can also see a DPS result, which is not conditioned on the sensor data. All right, that was the second part of my talk. So let me remind where we are. So I talked about plug and play priors, using denoisers as priors. First thing we did, we talked about blind inverse problems. And then I talked about diffusion models, but using conditional input of a sensor data, which boosts the performance quite a bit by giving additional source of information to the denoiser that we use as a prior. Finally, I have time to actually talk about the third model, which is going to be the doing inverse problems with continuously representing images, which is something we applied for microscopy. So it's very much in line with the same topic of using denoisers as priors. However, what we want to do is we don't want to use images predefined on pixel grids. Okay, so we want to represent images differently. And what we're going to do, we're going to take a nerve-inspired approach by taking implicit neural representation, where we're going to say, my image is going to be represented by a neural network that takes coordinates and gets a pixel value at the location, right? So this is a continuous representation now. I don't have to put the grid of vectors. I just need the weights to represent the images. Now, the key point of this continuous representation will decouple the solution from a predefined pixel or voxel grid, which could be advantageous in settings, for example, in very high dimensional settings for performing estimation. And then basically, we're going to use the same neural network at each location, just like in traditional nerve approaches. So that neural network will somehow also capture redundancies within the image, which can be interpreted as having some form of internal learning ability, although maybe that's a stretch, but there is definitely some regularization coming from the nerve itself. So let me just go directly and present this in a 3D case. The way we're going to do it is we're going to say, I have X, Y, Z coordinates. I'm going to put it into a neural network. That neural network will have, just like in a, well, I can give you details if anybody interested, or I'll see it in the paper. It has Fourier feature layer in the first layer, but then it goes through and it gives me two values, real and imaginary value, which will be the refractive index. So it's going to give me a real value of refractive index, imaginary value of refractive index. We're going to put this into minimization framework, where we're going to have B LED illuminations. We're going to put the model here. A will represent the forward model. Y will be the actual measurements. And then H theta here will have a denoiser written as this form of regularizer, where you can see where, okay, it's going to reconnect in a second, hopefully. Here we go. And then the regularizer here will be trying to push the solution to be close to the input and output of the denoiser together, which basically says when it's 0, you would see that the denoiser is not acting on the image, meaning it's not denoising the image, right? And by minimizing this thing, we're not going to minimize over pixel values. We're going to just minimize over the weights of implicit neural representation. So now that gives us formulation. We're not minimizing anymore over pixels. We're going to minimize over the continuous representation. But by finding now the solution, we get a lot more flexibility in some sense, because now, once given this representation, we can have it on a different grids. We can change the grids as throughout the optimization. We can sample, resample image at different moments. For example, here you can see this sample shown at 3.5 denser grid, 7.3 denser grid, or even closer denser grid. And you can see this, the flexibility of this kind of representation continuously. Let me show you some examples of this. So I'm going to skip this one. So this is an example of it on a real data. So this is diatom algae. It's a 3D sample. What I'm showing you is the image is going through slices. So this is going through axial optical axis. And one slice here on the left is a
the original reconstruction in IDT from 2019. We have more comparisons in the paper if you're interested. But you can see this approach, by using both denoiser and continuous representation, allows you to really get very sharp reconstruction in the Z direction, which is very interesting because of the missing angle in this thing. So I'm going to skip this. This is another sample. You can see going through Z, you're going to get very high quality reconstruction. I think this one is not moving, so I'm going to go here. So another interesting thing, because it's continuous, I can synthesize Z directions that are were not part of my original, say, it's not really training, but reconstruction, and synthesize complete frames like this one, which are going to be consistent with the model that's provided. So yeah, so I think this will be, let me summarize my talk. So my talk was basically about plug-and-play priors, which is using image denoisers. And using image denoisers, we can try to do several things. One thing we can do, just try to solve inverse problems by trying to go into fixed points, right? And this can be interpreted as kind of statistical estimator. I talked about blind inverse problems, where we train denoisers for each unknown, including the measurement model, so physics-based measurement model. Then I talked about using it as diffusion models to generate samples. So there you need to add some stochasticity. So having the stochastic ability, like in diffusion models, with a broader noise range reconstruction. And then you can start filling in missing data, for example, if limited angle tomography. Then I talked about using denoisers also in the context when you're representing your objects continuously, for example, by using implicit neural representations. Even in that case, you can now get this reconstruction, which will be the weights of the image, for example, in microscopy, and synthesize it on the grids that you care about as you go about. So I'll stop here, and if there are any questions, I'll be happy to take them.
If anybody has any questions, I can bring a microphone to you.
Okay, thanks for the talk. So my question is, it looks like in microscopic imaging, people more care about how small the subject we can see, which depends on the wavelength of the light, right? So it looks like if we use like a continuous, like a civil resolution, not like the story people in microscopy they care about. I mean, like a level of intuition where we work on like continuous mapping, not care about the physical wavelengths or some stuff, yeah.
Well, you know, depends on what you mean they care about. I work with many microscopic people. They care about all kinds of different things, including the resolution limit, which you mentioned, right, based on the wavelengths. Yeah. So it's a question that how the resolution limit plays with continuous representation, or is it why continuous representation if we care about resolution limit?
Yeah. I think here is like maybe two different aspects of super resolution. One super resolution is something like a digital camera, right? We have like more pixels. Another super resolution is from physical view, because we can see how small the subject of the object, yeah. Right? Yeah, so I asked some BME people, look, they say we more care about how small, like in tissue or some stuff we can see, like much more important than like from like pixel view, like how small the discretization error, yeah. Right?
Well, I understand where your colleagues from BME come from. Mm-hmm. You know, if you ask them now, try to tell them the resolution limit of a diffusion model generated image, that would be an interesting experiment, right?
Yeah.
So what's the resolution limit of diffusion model generated image? I mean, it's not anymore related to a physical property. It's based on the prior itself. You can generate very high resolution images, which could be seeing details beyond the resolution limit, but they might be fake, right? Okay. Yeah. So the question becomes very murky once we go to nonlinear models. So the intuition we have about the resolution limit of wavelengths, you know, Rayleigh limit, is very much related to, you know, how much I can separate two sources, but it's very linear view, right? So now, whether am I claiming that the continuous representation gives us super resolution? I don't entirely, because it goes out this linear view of explaining. But it does improve the axial resolution in the sense that we can see more in the Z. But it's potentially not because
we're adding higher frequencies in the measurement of them. It's because the prior is bringing that information.
Yeah. Okay. Thank you
I'm
very
happy
much.
to discuss more if you want.
Yeah. Thank you very much. Thanks. Yeah.
Hello. So my question is for like solving an inverse problem. What's your opinion about like using to maximize the posterior using plug-and-play denoisers versus training a sampler that you can sample from the posterior distribution?
For me, both could be done by training the denoisers.
Yeah, but I mean, to solve an inverse problem, do you care about like, more about like diffusion posterior sampling, where you want to find a solution that maximizes the posterior?
Oh, is it like a map versus MMSE question? Do we want to get so there's 3 ways. I can sample distribution, and I might care about distribution, like variance, uncertainty, quantification. Yeah. I might try to say maximize the posterior, right? That's statistically. Or I can try to say I want minimum mean square error, which is minimize the mean square error. Or I can do something else completely. So, but all of them can be tried to approach from statistical angle by using a denoiser. And my perspective is I find all of them valuable and very interesting. Yeah. I don't necessarily stick to one. I do like the simplicity of map interpretation. Usually if you care about PSNR or MSE, MMSE estimators will probably get you a better solution. But perceptually, by maybe sampling from posterior will give you,
Yeah, but for medical imaging applications, we always suffer from like we don't have a lot of data to train. So which way do you think is more suitable for training on a small data?
If you want, it's a trick question. There are many angles to answer. If you want, we can discuss afterwards, and I can tell you it would get a little longer. But depends on how much data. Yeah. Depends. But training the denoisers is definitely usually easier than training the full inverse problem solver, because now you'll have no self-supervision. Mm-hmm. So that's something there.
Hi, Dr. Kamilov. Thank you so much for the fantastic talk, and including not only diffusion and also the implicit neural representation learning. That's pretty cool. Yeah, I'm wondering that in your research work with the microscopic image within IRR, do you have came into some like the problem of like, for example, the memory issue? Because always a microscopic image is pretty large resolution and also large size, right? When you are using or train this INR model, do you come into like any problem when you're solving this kind of limited angle problem?
Yeah, so the memory issue is huge. In fact, the reason I picked up the INR originally, by the way, it's a great question, it was a hope that eventually through INR we can get some form of compression, in the sense that INR representation, the weights of that neural network would give you the memory you need to store that neural network, which can be decoupled from the XYZ-T, which means XYZ time number of pixels. And then by doing some form of block coordinate algorithm, I can just update based on subset of measurements and synthesizing things as I go, but just reduce the storage. There is some compression effect, but we didn't yet achieve a big compression effect. But the hope is, in fact, to look into this compression effect, to not run into the memory issues as much. Okay, so for this algorithm, we didn't run into memory issues, but we did run into the speed issues. It's pretty slow. So if you look at the paper, the limitation is the speed of the thing, because we need to go through INR, the physics forward model, differentiate back, update the weight, and so on. That was a key bottleneck in this one, but not the memory. But yeah, it's a delicate interplay there.
Yeah, I agree. The INR representation could be like more memory efficient, but during the training part, when you are using the physical form model and compare that with the supervision on the measurements, right?
Yeah.
For this part, you will get you to like have all the coordinates, all the pixel intensities on the whole image space. So if you include this part in the training part, do you think, is there any?
No, there's not everything, by the way. If you go to the paper, it's a block coordinate algorithm. So what we do is we just synthesize the part we're going to optimize over, take those measurements, and update the weights. And then pick another region and do the updates.
I see.
It's not, so the forward model in optical, in IDT is it's an optical setting, so that it's not one pixel to every. It's a kind of a decoupled model where we can efficiently update only parts of based on the parts of the measurements.
Yeah, I agree. I work on something with like cryo-EM, the electron microscopy, and we came into the same issue. So we're doing like the updating like slice by slice, like you mentioned. Yeah. So I think that is something, very interesting. And I will talk more with you offline.
We can discuss more about it.
Yeah, thank you so much.
Thank you for the question.
Can we have time for questions? Or?
Yep. Yeah, we can take
so
one more question.
So I have one more question. It's related actually to the previous talks too. Maybe you can give us some insight and related to that compression issue, right? What is the nature of the architecture? How do you get to the architecture? Is it relatively easy to get an architecture that works? What is the model selection process here?
Okay, so by architecture, you mean the denoiser architecture?
Yeah, the neural network.
The neural network. So, because there are two architectures here. The first architecture is the neural network I use as a prior. The second architecture is the inference architecture.
That's right, the neural, both.
Both, okay. Yeah. So the inference architecture is actually principled in many ways because it's based on the way I formulate my statistical estimation problem. So you can base it off like proximal algorithms. You can base it off gradient-based algorithms. They're all based on, in one way or another, built on existing algorithms people use for inverse problems by replacing component, which is a prior, by a neural network.
Meaning that it's a well-known architecture in terms of the size, in terms of like the number of layers, number of units?
Those are known, yeah.
Okay, I see.
What's less known is the CNN that's a prior. So it's a unit inside. So maybe let me, so if I go to give you just one example, right? So this one, Dolce. If I come here, it went off. Okay. This architecture, which is just part of the whole inference machine, is the one which is a trickier. There there's no intuitive way for me to select. The way I select, I can tell you, I look at some of the powerful architectures and they keep on evolving. For example, some work, DPIR, which is on powerful neural networks by Kai Zhang. His code is great and easy to use. We take one of those, we just train based off that. Unfortunately, I don't have much insight into this, but they have been evolving and improving.
Thank you.
So.